Good morning to all of you. In previous lecture, we have discussed about the line integral in complex plane. Today we will see some example related to the line integral in complex plane and also some more related theorems. Okay, so let's start. Question. We have to find the integral of the function z square along a curve C, where C is the arc of circle, where the C is arc of circle, z is equal to 2 from theta 0 to theta pi by 3. Okay, so we will write the equation in polar form because C is a circle about origin of radius 2. So here we can write parametric equation, polar equation for this circle. It will be r is 2 here, sorry, r is 2 here, ei theta, because this circle we have to take this circle when theta is lies between 0 to pi by 3. So theta will be lie here from 0 to pi by 3. Okay, now we can find dz here. Dz will be 2i ei theta d theta. Okay, so this integral say that it is I integral along C of z square dz. So this will be, when we are substituting z is equal to 2 ei theta square, dz will be 2 times I ei theta d theta, and this theta vary from 0 to pi by 3 for this curve C. So it will be 8i 0 to pi by 3 e2i theta plus ei theta into ei theta. This will give you 3 times I theta d theta. So after integrating it with respect to theta, you will get the required result. Okay. Okay, so next question is, we have to find the integral of equation Jn dz when n is 0 plus minus 1 plus minus 2 and so on. So we have to find integral of this function Zn when C is a curve of radius r about origin, and direction of this curve is traverse in counterclockwise direction. Counterclockwise direction. Like previously, we can also take here z is equal to r ei theta. This will be ei theta. and because it is in the counterclockwise direction, so this theta must be vary from 0 to 2 pi. This will be vary from 0 to 2 pi, and r is fixed here, so dz will be r I ei theta. This will be r ei theta. So substituting this value here, you can find because we will use this result in our next question. That's why I am proving it here. So it will be r ei theta to power n into r I ei theta d theta. Theta vary from 0 to 2 pi. Its value will be r to power n into r n plus 1 I 0 to 2 pi e to power n I theta into ei theta. This will give us n plus 1 I theta d theta. Okay, integrating this function, we can also write here. R n plus 1 n plus 1 I theta divided by n plus 1 I 0 to 2 pi 0 to 2 pi. This will be, so I will be r to power n plus 1 e I n plus 1 theta 0 to 2 pi. So its value will be e to power 2 n pi n plus 1, 2 pi will be 1. इसको चेक करिएगा, और n plus 1. This can also be write as cos n plus 1 theta plus I sin n plus 1 theta 0 to 2 pi 0 to 2 pi. So substituting this value here, cos for cos 2 and pi, when we are substituting this value, it will give you 1 minus 1 means 0 only when if it is a non-zero value. So it will be r n plus 1 upon n plus 1 into 0, and this will be 0 when this quantity is non-zero, any finite value. So this will be the finite value only for when n is not equal to minus 1, because when this n is when it is n is equal to minus 1, so this will be not defined for n is equal to minus 1. So integral value क्या है, तो यहाँ पे हमारी it will be not convergent. So that's why it is true. Its value will be 0 only for n is equal to minus 1. Otherwise it will be 0 by 0 form हो जाएगा, indeterminate form. So n is equal to minus 1, we have to evaluate the integral separately. So for n is equal to minus 1, value of this integral will be 0 to 2 pi z is equal to minus 1 dz. Z is equal to minus 1 dz means when we are substituting z is equal to r ei theta, it will give you 0 to 2 pi r ei theta to power minus 1, and dz will be I r into I theta d theta. So we will get I is equal to 0 to 2 pi 1 upon r ei theta into I r ei theta d theta. So this will be cancelled. We will get 0 to 2 pi I d theta, and after integrating it, we will get theta 0 to 2 pi. So 2 pi I. So value of the integral along the curve C, where C is a circle of radius r, of this function z and dz will be 0 when n is not equal to -1 and its value is 2 pi I when n is equal to -1. So this will be the value of this integral here. Next question is, we have to evaluate an integral c mod z is equal to integral of under root z is equal to dz, where c is defined as zt is equal to eit. This is eit, and t lies from 0 to 2 pi. T vary from 0 to 2 pi. So we have to integrate this function. Okay, so you know that under root z, yani z to power 1 by 2, it is a multi-valued function. We have already studied about this function in our some previous lecture. So for evaluating this function, integrating this function along this curve, we have to take its principal branch. We have to take its principal branch, or we can say that we have to restrict our t such that we will only dealing with a single valued function. Okay, so for this purpose, here our fz is under root z, which is a multi-valued function, is a multi-valued function. So we have to considering here its principal value for all t in 0 to 2 pi. So here our zt is exponential of it. So we have to take the argument like we are choosing argument for this function, for this zt. We are taking here, its argument is lie from minus pi to pi, because it is a multi-valued function. That's why for this function its argument is lies between minus pi to pi. इस तरह से ले रहे हैं. We are choosing here minus pi is branch cut. Okay, so या pi भी branch cut ले सकते हो, it's not a problem. For all t will come from the closed interval 0 to 2 pi. So we know that general argument for this function, general argument for this function eit is generally written as t plus 2n pi. 2n pi, where this n come from the set of integer, or we can say that it is plus minus 1 plus minus 2 and so on. Okay, so argument of t, we have to choose our t from this interval 0 to 2 pi such that argument of this function is lie in this interval. So argument of eit is when t lies from 0 to pi, when 0 to pi, बिकॉज हमें अपना प्रिंसिपल आर्गुमेंट ऐसा रखना है इसके लिए फंक्शन आर्गुमेंट e टू पावर आई टी के लिए. सो व्हेन t इज 0 टू पाई, इट मींस दैट 0 टू पाई मींस ये हमारा डायरेक्शन 0 टू पाई इस तरह से डायरेक्शन है. So in that case we have to choose the argument t. We will choose the argument t. Okay, so when t takes the value from pi to 2 pi, when t takes the value from pi to 2 pi, so it is 2 pi, when value is pi to 2 pi means यहाँ पे t जब हमारा vary करे, in that case we will read the value like this. In negative direction में value treat करेंगे. So in that case we can take argument corresponding to n is equal to -1. n is equal to -1 क्यों? मान लीजिए यहाँ पे हमारा t है, तो this angle we will read this angle by 2 minus t. इसको हम पढ़ेंगे, इस डायरेक्शन में पढ़ना है. या सॉरी, for suppose that our angle will be t takes the value like this. तो पॉजिटिव डायरेक्शन में t की ये वैल्यू है, बट वी वांट टू रीड दिस आर्गुमेंट इन नेगेटिव डायरेक्शन, सो वी हैव टू रीड दिस वैल्यू. एंड इफ दिस इज द t, यहाँ पे ये वैल्यू ले रहा है t, तो एक्चुअली जब नेगेटिव डायरेक्शन में पढ़ेंगे, बिकॉज वी वांट टू टेक द आर्गुमेंट इस इंटरवल में चूज करना चाहते हैं, क्योंकि हम ऐसा कर सकते हैं, इंटरवल 2 पाई लेंथ का अरेंज कर सकते हैं अकॉर्डिंग टू अवर चॉइस. सो इफ वी आर टेकिंग इन दिस लाइन, तो वी हैव टू टेक हियर, क्या करें अगर हम इस प्रिंसिपल लाइन पे लेना चाहते हैं. सो दिस t, this argument t can also be write 2 pi minus t, because this is t, this will be in negative direction. If we are reading angle in negative direction, this will be 2 pi minus t. So we can write here, और नेगेटिव एंगल लिखना है तो t minus 2 pi लिखेंगे, t minus 2 pi, because we have to read this angle in negative. So this will be t minus 2 pi when t is lies between pi to 2 pi. So argument for this function EIT will be t when t lies between 0 to pi, and its argument will be t minus 2 pi when t lies between pi to 2 pi. Okay. So corresponding the principal value of this function under root zt must be, its value must be, because zt was EIT, it was EIT. So when this t lies from 0 to pi, so यहाँ पे argument इसका क्या होगा t का, this will be t, so it will be under root zt will be EI t by 2. Okay. And when t lies from pi to 2 pi, because we are taking t is equal to 2 pi as a branch cut, so for this purpose, in argument for this function, principal argument for this function will be t minus 2 pi. So when it is t minus 2 pi, so under root zt will be EI t minus 2 pi divided by 2. This is divided by 2. It will be principal value for this function under root zt. So argument of this function in that case, so this will be the value for the function, whole defined principal value of this function for this t lies from 0 to 2 pi. Okay, now we can simply integrate this function. So first of all, we have to find dz by dt. So dz by dt will be here, dz by dt will be integrating with respect to differentiating with respect to t. It will give you I by 2. Okay, dz by dt, this will be I times EIT when t lies from 0 to pi, and when t lies from pi to 2 pi, its value in place of t, it will be t minus 2 pi. So this will give you I EI t minus 2 pi. So this will be dz by dt. Okay, so we have to integrate 0 to 2 pi under root zt dt. So this will be zt into dz. Sorry, this will be dz. This can also be write as 0 to 2 pi under root zt dz by dt into dt. So we will we will split this whole interval of integration first from 0 to pi, then pi to 2 pi. So interval of integration will be 0 to pi, then pi to 2 pi. Now substituting value of under root z for this when t lies from 0 to pi, it will be e to power I t by 2, and dz by dt will be I into eit dt. And from pi to 2 pi, under root zt will be e to power I t minus 2 pi upon 2, and dz by dt will be I times e to power I t minus 2 pi into dt. Simply integrate these two integral, we will get the required result. After integrating these two integral, we will get the required result here. Okay, so कर सकते हो, ये सिंपली कर सकते हैं, इसको कर लीजिएगा, बताइएगा आंसर क्या आ रहा है. ओके, one more thing. For suppose that we have a curve C, so if we want to find the length of that curve, so if for suppose that zt is the curve from interval to this C, so length of the curve C, length of curve C is given by क्या होता था, mod of z dash t dt. एक्चुअली mod of dz होता था, उसी को लिखा है mod of z dash t dt, and when t lies from a to b. So this will be the length of this whole length of this curve C. Okay. Next is simply connected domain. What is simply connected domain? You know already about the connected domain, connected region. Here we will study about simply connected domain. What is the simply connected domain? A connected domain is said to be simply connected connected domain is called simply connected domain. Simply connected domain if every closed curve inside that domain, if every closed curve inside that domain includes is only the point of domain, only the point of domain, or we can say that if we are drawing a simple closed curve inside that domain, so if we are shrinking this curve, so this curve will be shrunk to a point inside that domain without leaving that domain. So for suppose that domain name is D, so if we are drawing any simple curve which lies in D, in domain, we can also say that domain can be shrink, that curve can be shrunk to a point without shrunk a point inside the inside domain without leaving the domain means, for suppose that we have a domain like this. We have a domain like this, and inside this domain, जितने भी points हैं, all the points inside it is the points of this D. या कहें कि if we are drawing a simple closed curve, if we are drawing a simple closed curve, this is the curve C. If we are drawing a simple closed curve inside this domain D, if we are shrinking this curve, अगर मान लीजिए इस curve को shrunk करें and shrunk करके it will become a point. So that point will be a point of this D, and in that process this curve will never leave this domain D. So that kind of domain is called simply connected domain. या simple word में बोले, for example we have a, मान लीजिए for example we have a piece of paper, एक piece of paper है, and in this piece of paper there is no hole. If there is no holes, इस तरह का अगर नहीं है, so this paper is called simply connected domain. अगर उसमें ये बोल सकते हैं, ये भी in simple language we can say that a domain which does not contain any holes, because for suppose अगर यहाँ पे कोई holes है, for suppose this is our domain और यहाँ पे ये एक hole है, hole को हम इस तरह से दिखा देते हैं, because for suppose that this is the hole inside this domain D. Say that it is domain D. Inside this domain it is hole. इसका मतलब इस hole के अंदर जो points हैं, they are not the point of this D. D के points नहीं है, they are outside. These points are lie outside of this D, because D केवल हमारा ये portion है, ये portion. This is our D. Okay, but D is containing the point outside of this D also. इसके अंदर ये points भी दिख रहे हैं. And for suppose that अगर एक क्लोज कर्व हम ड्रॉ करते हैं इनसाइड दिस D, फॉर सपोज दैट एक क्लोज कर्व हमने ड्रॉ किया, दिस इज आवर क्लोज कर्व, सिंपल क्लोज कर्व इनसाइड विच इज लाई इनसाइड दिस D. So if we are shrinking this curve, if we are shrinking this curve to a point in D, मान लीजिए इस पॉइंट पर या इस पॉइंट पर हम कर्व को श्रिंक कर रहे हैं, कर्व को श्रिंक करके समेट के हम इस पॉइंट पर ला रहे हैं. So without leaving this D, this curve cannot shrink to this point, क्योंकि इसमें जब ये श्रंक करेगा तो ये यहाँ पे इसको पास जरूर करेगा, इसको जरूर कट करेगा. सो ये D के बाहर एक बार इसको जाना ही होगा. तो विदाउट लिविंग दिस D, we cannot shrink to this curve at a point in this D. So in simple word we can say that a region without any hole is called simply connected domain. And multiply connected domain, a domain which is not simply connected, that kind of domain is called multiply connected domain. Next important theorem is Cauchy integral theorem. Cauchy's integral theorem. Suppose that fz is an analytic function and f dash z be a continuous in a simply connected domain D. Let fz be an analytic function and derivative of this function f dash z be continuous in a simply connected domain D. Then integral along this curve C fz dz, then integral fz dz always be 0 for every curve C lie inside this domain D. So along then this integral will be 0 along every simple and close, simple, smooth and close curve, simple, smooth and smooth or piecewise smooth or piecewise smooth and close curve, C lie inside D, lie in D. So if fz is analytic function and its derivative is also continuous in a simply connected domain D, then when we are integrating that function along any simple closed curve, which if this curve is lie inside this domain D, so that integral will be 0. So this statement is called Cauchy integral theorem. So now we will prove this theorem with the help of Green's theorem. Okay. Suppose that we have a domain D, and inside this domain we are taking a curve, simple closed curve C. Direction is where we are taking only the positive direction here. So here D be a simply connected, let D be a simply connected domain, simply connected domain, and C is simple, smooth, closed curve and closed curve inside domain D. Okay, you know that fz is a complex valued function, so we can write this as u xy iota v xy plus iota xy. So integral fz dz along this curve C can also be write as, in place of fz we can write u plus iv. So close curve hai, so we can also use this symbol. If you are putting this symbol, it's okay. If you are not putting it, okay, it doesn't matter. Okay, so we can write here, in place of fz we can write u plus iv, and in place of dz, because z is x plus iy, so dz will be dx plus I dy. So then we are calculating it. It will give you u into dx minus v into dy plus I times u into dy plus v into dx. And this can also be, if we want to represent it in real and imaginary part separately, so we can also write it u dx v dy plus iota integral along C v dx plus u dy. Say that it is expression number 2. This is expression number 2. Now we will use here the Green's theorem. So what the Green's theorem says, and you know that fz is analytic in domain D and f dash z is continuous in domain D. So obviously f dash z, if f dash z is continuous, it means that uh, derivative of this function u and v, first order derivative of these two function, will be also continuous in D, because you know that f dash z will be del u by del x plus iota del v by del x. And if you are using CR equation, you can also represent f dash z as a derivative, partial derivative of u and v with respect to y also. So you know that if f dash z is continuous, so its real and imaginary part, which are the partial derivative of u and v, that must be continuous. क्योंकि हम जानते हैं, हमने पहले पढ़ा है, अगर फंक्शन एफ जेड कंटिन्यूअस है तो यूएस और यू वाई भी कंटिन्यूअस होते हैं. एंड एफ डैश जेड अगर कंटिन्यूअस है तो उसके रियल इमेजिनरी पार्ट हमारे हैं डेल यू बाय डेल एक्स एंड डेल वी बाय डेल एक्स. सो ऑब्वियसली दे विल बी ऑल्सो कंटिन्यूअस. So we know that because f dash z is continuous in domain D, that's why the partial derivative of real and imaginary part of this function fz must be continuous in domain D. Okay. So Green's theorem says that, because we are using here the result of Green's theorem. So Green's theorem says that if we have two function phi and psi, both are the function of two variable x and y. So we have two functions, say that phi and psi are continuously differentiable function. Continuously differentiable functions inside a region R, and also on the boundary of this region R. Say that boundary is denoted by here this gamma. This is denoting the boundary of this R, boundary of R. Then Green's theorem says that line integral along the boundary of region R of the function phi dx plus psi dy is equal to surface integral over region R of the function del psi by del x minus del phi by del y dx dy. Say that it is equation number 3rd. We will use this theorem, statement of this theorem, in our previous equation, which was the equation number 2. So you know that u and v are the function whose partial derivative is also continuous. So it is continuous partially. So function is continuous partially. So we can write, क्या थी हमारे पास second equation, u dx v dy. So by the Green's theorem, we can write here, if we can replace it by, say C के अंदर जो region है, say that it is R. C is the bounding the region and we denoting this region by R. For suppose that the region bounded by this curve is denoted by R. So simply we can write here, this is our phi function and it is our psi function. So by using the Green's theorem, we can write here, पहले हम इस इक्वेशन को वहां लिख लेते हैं. Equation 2 was fz dz is equal to u dx v dy plus iota v dx plus u dy. Using this result here, we can replace it by double integral or surface integral over region R. Region R is bounded by this closed curve C, and we can write here del by del x of minus v. Of minus v means we are writing here minus del v by del x. minus time del u by del y into dx dy plus iota surface integral over region R. This will be, for this function, it will be del u by del x minus del v by del y dx dy. Say that it is equation number 4. Say that it is equation number 4. Because fz is analytic function, so it must satisfy CR equation, and CR equation says that del u by del x is equal to del v by del y, and del u by del y is equal to minus times del v by del x. So using it here, so minus time del v by, in place of minus time del v by del x, we can write del u by del y. Here we can write del u by del y. So plus del u by del y minus del u by del y will cancel each other. So we will get here 0. Again, in place of del u by del x, we can use del v by del x. Del v by del y. So by CR equation, both the integral on the right hand side of this equation 4 will be 0. So both the integral, by using the CR equation, in 4, we will get line integral of fz dz will be 0 plus iota 0, that will be 0. So hence we proved the statement of Cauchy integral theorem. So Cauchy integral theorem is proved here. Okay. In the statement of Cauchy integral theorem, we says that fz is analytic in simply connected region, and f dash z is also continuous in that region. But this condition of continuity of derivative of this analytic function can be dropped. This condition can be dropped here in Cauchy integral theorem, and in that case, result of Cauchy integral theorem will be obtained by using a lemma, and after that this theorem is called Cauchy-Gorset theorem. So Cauchy-Gorset theorem says, by using a lemma without using the condition f dash z is continuous in a simply connected region, we will obtain the same result, and then this theorem is called Cauchy-Gorset theorem, because after the Cauchy-Gorset also work on it and give an improvement in this theorem, modification in this theorem, and that theorem is called Cauchy-Gorset theorem. This theorem says that if fz is be an analytic function in a simply connected domain, connected domain D, then line integral of the function fz dz will be 0 along every simple closed and smooth curve in D. Along every simple closed and smooth or piecewise smooth curve C in D. So in this theorem, we have dropped the condition f dash must be f dash z should be continuous in this domain D. So without using that condition, we can also prove the same theorem. Okay, so some question based on Cauchy integral theorem we will use here. We have to evaluate an integral along a closed curve C of the function 3z plus 5 z square plus 2z dz, where the C is a circle of radius 1 about the origin. Okay, so our reason is it is a circle of radius 1. Say that it is our circle of radius 1. Okay, where it cut the x-axis, it will be 1, this side minus 1, this one is will be iota, and this side it is minus iota. Okay, so this function fz can also be write as 3z plus 5 z square plus 2z. This can also be write as z plus z into z plus 2. Now writing is partial fraction. So suppose that z and z plus 2. So what we should write here? Because we want here 3z. So z plus 2 and z. Z plus 2 plus z only give you 2z plus 2. We want 3z. 2z. Okay. This will be 1. 5z plus 10 plus z divided by 2. Okay. So this will be the partial fraction here. So obviously you know that if function is a rational form, so it is analytic everywhere except the point where denominator is 0. So we are writing this fz like z 5 upon z plus 1 upon z plus 2. So this part, you know that this part will be not analytic at z is equal to 0, and this part will be not analytic at z is equal to minus 2. So this is our curve C. We are taking in contour is taking in positive direction. So z is equal to 2 means z is equal to minus 2 will be lie somewhere this side outside of our curve. So this function is 1 upon z by z plus 2. This function is analytic everywhere and also on on this curve C. This part of function 1 upon z plus 2. This function is not analytic only at this point z is equal to minus 2, which is lie outside of this closed curve C. So obviously 1 upon z plus 2, it is a rational function. It will be analytic at every point inside this C and also on the boundary of this closed curve C. So this function is analytic everywhere for this curve C. But this part of the function 5 upon z, this function is not analytic at z is equal to 0. So if when we are integrating this function fz dz, this can also be write as 5 by 2 1 by z dz plus 1 by 2 integral dz upon z plus 2. Say that it is integral I1 plus integral I2. So obviously by Cauchy integral theorem, value of this I2 will be 0. Now we have to evaluate integral I1 because 0 function is not analytic inside this closed curve C. Okay. अभी हमने पिछले एक एग्जाम्पल पढ़ा था कि for this function its value will be 0 when n is not equal to minus 1 and when n is equal to minus 1 its value is 2 pi I. यही वैल्यू थी. तो सेम वे में यहाँ पर भी हम इसको जो है इवेलुएट कर सकते हैं 1 dz upon z because n is equal to minus 1 here. So when we will evaluate it, its value will be 2 pi I. जैसे हमने previously evaluate किया था, same manner you have to evaluate it. So its value will be 2 pi I. And I1 will be here 2 pi I. Sorry, it was 5 by 2. So this will be 5 by 2, 5 pi I. Value of I1 will be 5 pi I. But I2 will be 0 by using previous theorem, which was Cauchy-Gorsuch theorem. By Cauchy-Gorsuch theorem, I2 will be 0 because this function is analytic everywhere inside and also on the boundary of closed curve C. So its value will be 0. So finally, value of the integral I1 plus I2 will be 5 pi I plus 0. So 5 pi I will be our final value here. One more small topic on it. For suppose that function fz is analytic in a simply connected domain D. For suppose that this is domain D, it is domain D, and function fz is analytic everywhere in this closed in this domain D, simply connected domain. D is simply connected domain. If we are taking any 2 points inside this domain, say that it is z1 and z2. This is z1 and z2. Okay, and we are joining these 2 points by 2 paths. Say that one path is this C and another path is this path D. Okay, we are taking 2 points inside this simply connected region z1 and z2 and joining these 2 points by the 2 path. One path is C, another path is D. Okay, so if fz is analytic inside this domain, then when we are integrating the function fz dz along any path, along any path, maybe it is C and also this path D, which is joining this z1 and z2. So value of these two integral will be same. Value of these two integral will be same. If function is not analytic, in that case, value maybe this value is not same. It will be the part dependent. But if function fz is analytic, then value of this integral will be the same. It will be not depending upon which path we are using here to join this z1 and z2. Its value will be depend only the end points, z1 and z2 points, these 2 points. It will be not depend upon the path by which we are joining these 2 points. Okay, so this is one more important topic, and we can prove it simply by using Cauchy-Gorsuch theorem, because we can take this point totally. इस पॉइंट को एक साथ इस तरह से ले सकते हैं कि ये जो पाथ हमने पढ़ा हुआ है, we can read this path like, for suppose z1 is point A, say that this is point A and this is the point B. So we can read it like a closed curve ADB CA. So when we are integrating the function fz along the closed path ADB CA dz. So because function fz is analytic everywhere inside and also on the boundary of this closed curve, so its value will be 0 by using Cauchy-Gorsuch theorem. And this path can also be right in we can break this path into path, because we know that when we are evaluating the integral, and if a path C is made by joining the 2 paths, so this can also be right as ADB plus BCA, FZ DZ and FZ DZ. Okay, and you know that this reverse path BCA can also be right as minus time ACB, ADB, FZ, DZ. From here, this is the path D and this is the path C. This will imply that integral along the D path ADB fz dz must be equal to fz dz when we are integrating it along this path C. So यहाँ से ये हम simply we can prove it. So if a function is analytic in a simply connected domain, so when we are integrating this function between 2 points, so in that case, integral will not depend upon the path we are choosing to join these 2 points. It only depends upon the endpoints. Okay. So now I am concluding this class.